We already calculated these two equations, del square V plus partial this one and this equation from Maxwell's equations, and we have reduced the Maxwell's equation and these two, which has potentials V, scalar potential and vector potential. We also know that B is equal to this and E is equal to this, and this gauge and variance, it means that this is a gauge and variance. Gauge and variance means that if we change V and A, then no change will occur in electric field and magnetic field. So we know about this. Now the question is, these two equations, we have to solve these two equations for V and A. So equation A contains both V and A, where these equations are coupled equation because V is here, V is here, A is here, A is here. So these are coupled equation. We need to find these equation to find V and A. We are interested to find the scalar potential and the vector potential, but in the present form, it is difficult to solve. To solve these equations, we need for some approximation. These are Coulomb gauge and Lorentz gauge. It means that we have to solve these two equations, but it is very difficult to solve. Now we are looking for some approximation to solve these two equations. The first approximation is the Coulomb gauge and the other approximation is the Lorentz gauge. Let's see next. The first approximation to solve these two equations, here we use the Coulomb gauge. According to Coulomb gauge, we specify the divergence of A, which is equal to 0 in magnetostatic. So we use this approximation, and this is the gauge, the Coulomb gauge, and we will put this approximation in equation this and this and find out the value of A and V. Let's see how is it possible. So consider the first equation 1 of A. So this one, del square V plus partial divided by partial T, if I consider this is equal to 0, which is equal to minus rho divided by epsilon naught. And this is del square V, which is equal to minus rho divided by epsilon naught. And this is nothing but this is the Poisson equation. This is the Poisson differential equation. And this is the second order differential equation, and this is very easy to find out the value of V from this equation. So this is one thing that we have calculated, and this is del square V, which is equal to minus rho divided by epsilon naught. By using this condition. From this Poisson equation, this is the potential and this is the potential at the left hand side, and this is the source. And if we change rho, then we will see the effect on V. And this is true in electrostatics. This is true in electrostatic. Because the electric field and electrostatic del V minus partial A divided by partial T. If we ignore this term, if we ignore this term in electrostatic, then we will get E is equal to minus del V. In electrostatic, we can ignore this. And we can say that if we change the source, then the effect will occur in this. But in electrodynamics, if we ignore this term, in electrodynamics, then it shows that one charge affect any other charge instantaneously, which is impossible in electrodynamics. I will write down if we ignore partial A divided by partial T in electrodynamics, then it shows that one charge can affect any other charge instantaneously. Which is impossible. Because this violates the special theory of relativity. We know the signal can move with maximum speed of light via C. In electrodynamics, if we find V, then it is only the particle of E, which is equal to minus del V minus partial A divided by partial T. And this term, this is very, very important term. This term shows the delay of signal which moves from one point to another. By adding this term, we cannot violate the special theory of relativity. The summary of this is we have the electric field which is equal to minus del V minus partial A divided by partial T. If we ignore an electrostatics, then it means that if we change the rho, then instantaneously we can change its effect. We can see the effect on V instantaneously. And it is true. But in electrodynamics, we have electric field which is like partial A divided by partial T, and this shows the delay, because if and after divided by partial T shows that this delay time. So we cannot ignore this term partial A divided by partial T. If we ignore this term partial A divided by partial T in electrodynamics, then it violates the special theory of relativity. Because after some time, this signal will reach to this point where we can calculate the electric field. So it is very, very important to know about this, that in electrodynamics we cannot ignore this term. This is a delayed term, and if we don't ignore this term, then the special theory of relativity cannot be violated. Further, equation 2 of equation A. Now we are interested to find the vector potential using the Coulomb gauge. Then we will consider this is equal to 0. And by considering delta divergence of this is equal to 0, then the new equation del square A plus minus mu naught epsilon naught partial square A divided by partial T square minus this del, this will be equal to 0, then mu naught epsilon naught partial V divided by partial T, which is equal to minus mu naught J. From this equation, if we find V from this equation, from this Poisson equation, from Poisson equation, and putting the value of V in this equation. The above equation means this equation. One can find out the value of A, but it is still very difficult. If we find V from this equation and A from this equation, then after this we can find the magnetic field, which is equal to del cross A, and the electric field, which is equal to minus del V minus partial A divided by partial T, because all the information are present here. A, we can find this from A from this equation, and V from this equation. Then after that we can find out the electric and magnetic fields. So this is the Coulomb gauge, and this Coulomb gauge, one thing is clear: we can find out the scalar potential very easily from the Poisson equation. But this is still very complicated to find the value of A. So now we are looking for some other gauge to find the value of A and V very easily.